You guys are good partners. You have the data. Data is power.
Okay, all right. We're going to get started. So please settle down so we can have our wonderful speaker, last speaker of the day and the summer school, Professor Schmiedeler from University of Notre. Notre Dame was in news some time ago, the one in France, for wrong reasons, the fire.
Oh,
yes. So he's going to be talking to you about optimization problem in mechanism synthesis. Is that right, Jim?
Maybe.
Yes, okay, go ahead.
I changed my mind a little bit.
Yeah.
Thank you all. I apologize for being loud and for arriving late. I just landed this morning, and I hope everyone's planning to come to St. Louis in 2020, where Andreas Mueller, who you heard from, will be the general conference chair, and I will be the program chair. We're very excited about the opportunities there. When I was putting together this talk, I was planning to talk primarily about optimization-based synthesis. I think you've already heard quite a bit about that from a machine learning standpoint. I was going to talk about maybe the counterintuitive idea of shrinking the search space to find better mechanisms. But that's not really what I wanted to talk to you about in retrospect. And so as I was putting it together, I wanted to talk more about a philosophy of approaching problems in the kinematics community. And so instead of doing that, I'm going to talk to you first about walking. Because I also do research in walking, as unlike some other people in this room, it has nothing to do with mechanisms directly. But I hopefully you'll see it as a case study for making the philosophical argument that I want to make today here on the last 20, we'll try to end early, 30 minutes of the workshop. So the philosophical question I want to ask is, are we solving math puzzles? Because I think this is, I love math puzzles, by the way. Math puzzles are fun. And I have solved math puzzles as part of my research. I will probably continue to solve math puzzles as part of my research. But I think it's a pitfall that the kinematics community has fallen into on occasion of solving math puzzles that aren't necessarily engineering problems. And so my hope today is that, not that you'll understand anything about my own personal research or its shortcomings, but that as you pursue, particularly as a graduate student, as you pursue your own research, you're thinking about this question: am I solving a math puzzle, or am I solving an engineering problem? And where I think our community has interesting contributions to make and pitfalls to avoid is at what point those two cross over. Because a math puzzle can look like a math puzzle and turn into an engineering problem solution. And what looks like an engineering problem solution can work out to be nothing but a fun little math puzzle. And hindsight is often 20/20, and it's easier to identify these things in retrospect, but I think a healthy dose of identifying them in your own work as you go certainly is helpful to me. So, example, the general Goff-Stewart platform problem. So in 1993, my friend and former colleague Madhu Raghavan, who many people in this room know, wrote a paper showing definitively via homotopy methods that I think you heard about some today, that the Stewart platform of general geometry has 40 configurations. This was a seminal paper in our field in terms of spatial mechanisms and robotics. If you look on Google Scholar, this paper has 414 citations. That's more citations than any paper published by all of the people who have spoken to you in this workshop, except 3 papers. Sunil Agrawal has 2 of those papers. Larry Howell has the third paper from Larry Howell's PhD work with Schmiedeler. The Stewart platform of general geometry has 40 configurations. Okay, the Stewart platform of general geometry does not have planar requirements on the attachments of the spherical joints here at the top platform. It doesn't have requirements on planar attachment points of the universal joints at the base. There's no symmetry to the top. There's no symmetry to the bottom. It's the most general version of the Stewart-Goff platform you can possibly imagine. Have any of you ever seen a practical Stewart-Goff platform of general configuration, general geometry? My argument to you today is this paper, which has been cited extensively and is a very well written and very clever piece of work, with almost 30 years benefit hindsight, I think this is a math puzzle. Shinwen, do you agree?
I think it's just some cases where your recommendation support forces. General story.
Is it completely general?
It looks like the structure, right? But it's not necessarily.
But it's not necessarily. And so did arriving at that design, so Sunil Agrawal has used completely general Goff-Stewart platforms, which is great, right? Did arriving at those designs require you to know that there were 40 possibilities?
No.
And so if you can get to that design without solving the problem of how many various configurations are there of the general Stewart-Goff platform, my argument is still, in retrospect, this is a math puzzle. It's not an engineering problem. At the time this paper was written, I think this was very much an engineering problem. Right? We didn't know how many configurations there were for a general Stewart-Goff platform. We imagined as designers perhaps that there were lots of applications that we might discover for these things if we knew everything about them. And so my comments here are in no way a condemnation of this really excellent paper that enlightened people to the use of homotopy methods that have gone on to have significant impact. But if you were to say, well, if this problem had remained unsolved today, in light of Anurag's machine learning talk, is it worth solving? Sure, it's worth solving. It's worth solving if we care about math puzzles. But I don't think it has real impact on engineering problems. Because Shinwen, right, who works in parallel mechanisms, identifies Sunil's designs as being of this nature.
Some cable-driven system.
Cable-driven systems, yes, right, are also general. But do we need to know that there's 40 configurations? So a very well-cited paper in our community, right, in the modern time is essentially reduced to an elegant math puzzle. Planar synthesis of finely separated positions, right? We've got up to 5 for a 4-bar linkage. And linkages are great, right? If you're a kinematician, I love designing mechanisms. I love to design the mechanisms. We're designing for irregular motion. If we're designing for regular motion, we don't need a traditional mechanism. You could do it with a single joint, probably, right? And I think Anurag already got to this point of like, how many applications exist where I really care that I exactly hit all 5 of these positions? The reality is exactly hitting these positions is a convenient way of framing the motion generation or the function generation problem or whatever you have, particularly a legacy way of framing it, because at the time we originally solved these problems, Freudenstein solved some of these problems, right? We didn't have the computing capability that we have today, and so you needed analytical solutions. And analytical solutions are beautiful, and they're elegant, and in many cases they introduce insight to the problem that we wouldn't have otherwise. And I'm not slamming exact position synthesis. I've done some work like this myself, right? All I'm saying is if we as a community are going to require that we hit our positions exactly, we need to be honest with ourselves about what's the engineering benefit of that. And the engineering benefit ought to be, well, I'm designing mechanisms that are more clever or more interesting or some other better approach that I get out of requiring exact position matching. Because with the modern computing techniques, right, we can do approximate matching of positions and have 50 of these things and more tightly control the motion we want to generate. There are trade-offs in each of these cases. My argument to you is, in the constraints that you put on your design, make sure those constraints are serving the engineering problem and not just facilitating a math puzzle. Okay, so this is what I want us to think about. Case study within my own work that has nothing to do with mechanisms, right? Walking. So I happen to work on walking robots, and I happen to do some human rehabilitative walking, and I happen to work more recently on exoskeletons that nicely brings together the robot walking and the human walking. And the bottom line is really, walking is walking, right? The mechanics of walking are what they are, regardless of whether you're dealing with a robot or a person. You're just changing the control system, in essence. And what's the engineering problem of walking? Well, why do we want to have legs? Legs are good for uneven terrain, right? So if you don't have uneven terrain, your mobile robot might as well have wheels. Or at least if you're not in a human design environment with stairs. And so the engineering problem of walking is locomotion over uneven terrain. Now, it's true that all of us walked into this building and into this room, and the terrain is relatively even except up here, right, where we've got some cords taped down, etc. And so there are sections of the world that are perfectly flat. But if most of the world is perfectly flat, we should all be on wheels, right? And the killer problem in walking is what Avengers gets right. I don't know about you, but I like it when science fiction gets engineering problems right. So the whole trick to Iron Man and the Avengers movies is this little heart fusion science fiction reactor that generates a ridiculous amount of power in a very, very small package, right? Because the killer problem for any mobile robot, but especially a legged mobile robot, is power consumption. And so we want to operate on uneven terrain, and we want to not consume a whole ton of power, right? Those are basically the two fundamental challenges of walking. And so, history of walking robots, if you're not familiar, so you've got passive designs like this that were developed by Tad McGeer. Passive in the sense that they consume no power except walking down slopes, so they consume a small amount of gravitational potential energy. In terms of energy efficiency, they're about the best you can do, even if you account for the small amount of potential energy lost, right? Very, very efficient, but not at all robust. Their disturbance rejection ability is almost non-existent because they have no actuation. In contrast, right, we have humanoids like ASME that are terribly inefficient, particularly compared to human walking, but much more robust than these designs because they've got power ankles and can reject disturbances. And so, right, in terms of how these systems deal with the engineering problems of walking, we have the extremes. We have super efficient, completely not robust, and significantly more robust at the expense, to some extent, of efficiency. And so we have the passive and then the fully actuated. And in my own research, what I've done is, and maybe you can sense this already from what I care to talk to you about today, is I'm a shoot-in-the-middle guy, right? So under-actuated robots have some actuation, but in this case, no ankle actuation to provide a torque at the ground. And so my argument is shooting in the middle. Well, maybe we can deal with some of the efficiency benefits of the passive systems and still get some of the robust benefits of the fully actuated systems. The challenge on the robustness side is I know how to define stability very easily not very easily, but relatively easily for a passive system, right? I can look at the Poincare return map of the inverted pendulum dynamics, and I don't have to worry about the control system, and I can tell you whether the system is stable. And if I have full actuation, including at the ground, well, I've got an actuator for every degree of freedom. There are a variety of ways I could design controllers that are guaranteed to be stable or provably stable, within friction limits and actuator limits, etc. And so the challenge is, I'm a shoot-in-the-middle guy. When I'm operating with the under-actuated systems, I can't directly use the method of Poincare for a passive system to analyze stability, and I don't have the actuation that I would need over here. And so I need some other approach if I want to guarantee robustness. And that's where I'm getting at with math puzzles in walking. I don't really care whether I guarantee robustness or not. I just care that the robot doesn't fall over and doesn't consume a ton of energy. But in the same way that designing a mechanism, I'm searching for a solution that meets some performance criteria. In designing a controller, I'm searching for a controller that meets some performance criteria. In this case, the performance criteria is the robot doesn't fall over. The math puzzle is, well, if I can prove my controller is stable, I've solved a math puzzle that also contributes to the engineering problem, right? And so I'm going to start with the math puzzle quickly, and then I'm going to talk about how we use the math puzzle, but we reject the sort of provable aspect of it, which I think is a similar case study with what we've used in mechanisms. So, okay, provable stability. So, if you imagine I've got a 5-link biped that looks like this, well, I said if we had a passive system, I could analyze the stability using the method of Poincare. Well, if I look at this red line from the point of contact with the ground to the hip, well, that's the passive part of this system, right? My robot here has actuators at the hips and the knees and no actuators here at the ankle. And so this theta degree of freedom is what I can't control. It's the unactuated degree of freedom. So if I just look at the red line, that's an inverted pendulum, right? And I said, using the method of Poincare, I can guarantee stability of pendulum dynamics. So I take my control problem here, and this was originally developed by Jesse Grizzle's group at University of Michigan, and I basically jump through enough hoops to enable my actuated system here to be analyzed for stability only in terms of the unactuated element, the unactuated degree of freedom. And the way I do that is, okay, I say, well, I'm going to assume that I have continuous dynamics during stance, which is a pretty solid assumption. And then I'm going to assume I have instantaneous transfer of support when my new leg touches down. So I have no period of time where both legs are actually on the ground. I have an impact that changes support legs. That's a lie, right? That never happens in reality. In the same way as when we design our mechanism to pass through 5 positions and we build it in hardware, it never exactly passes through the 5 positions, right? As soon as we go to the real world, there are deviations from the model. And so I have no robot that can instantaneously transfer. But by enforcing an impact map, right, so continuous dynamics, traditional form, impact map, change in velocities without any changes, instantaneous change in velocity without any change in position, I can achieve guaranteed stability. So I jump through the zero dynamics. Basically means, okay, if I have no errors at my hips or knees, so I control the shape of my robot in the air, the leftover dynamics are the zero dynamics. And those leftover dynamics are the dynamics of theta, that unactuated coordinate, how far the pendulum of the robot falls forward. And so what I end up controlling is the shape of the robot as it's falling. And if I control that shape reliably, right, the new swing leg comes in and touches down at the right position for the next step. And it's hybrid because I have this impact map that translates one stance leg into the next stance leg with each touchdown. And okay, we can do some manipulation to cancel the nonlinearities, and you don't really need to know about the mathematics. The whole idea here is this. actuation is a function of step progression. So as the student pushes the robot forward, the hips and knees are modified to control the shape of the robot as a function of how far that inverted pendulum motion has taken, right? It's not a function of time. This is the same motion played on a clock as if it were a wind-up toy, which it's not. And so with this, the idea is, okay, I'm analyzing the zero dynamics. So the zero dynamics, if I change the coordinate from theta to this c parameter here, I plot the position and the velocity of that unactuated dynamics. And you can see here, this curve is the nice continuous dynamics while I'm on the ground. And then I have a jump condition where I hit the ground and I have an instantaneous change in the velocity, and the change of position is reflected by the fact that now it's a new leg on the ground. And, okay, you don't really need to worry about all of this, but we go through the nonlinearities and we can make some provable statements. And really the important part here is, okay, I've got algebraic map, yada, yada. Here's the idea, right? I've got a periodic cycle. So I take a step, I evolve on my continuous dynamics, my new leg touches down, I bounce back, and if it's periodic, I come right back to the position with the next leg, and I repeat. And so the stability analysis that we're doing is, well, okay, well what happens if I start with an initial condition that's away from that periodic gait? So I'm in light blue now, and we see, okay, well I evolve on my continuous dynamics, and then I have my impact when my new leg touches down, and I bounce to a different location. And just as you would imagine, if you bounce to a location that's farther away from the periodic cycle, you're unstable. Whereas, instead, if I were to bounce to a location closer to my periodic trajectory, I'm stable because my errors are shrinking instead of growing, right? And so we basically can go through the proof of how do I find gates that enforce this stability under the assumptions of the model. And if I do, then I'm provably stable. And so and then I can project that provable stability for this simple system up to the fully actuated system, which is great. And the result is something like this. So you can change the size and shape of the foot, and the robot walks in a nice repeatable manner, and you get provable stability. Now, what I'm trying to tell you with all this is the hoops you jump through are the solution of a math puzzle. However, in this case, I find it to be a solution of a math puzzle. It solves a great engineering problem because these controllers, when you put them on the robot, they just work. And the solution space for all possible controllers that might work is quite large. And it's hard to know a priori without a provable stability whether they'll work or not. Here's the problem. I argued to you earlier that the whole point of walking is to be able to walk on uneven terrain, right? As soon as I'm on uneven terrain, I've lost provable stability. And so this idea that, okay, a provably stable gait is great because it works. We want it to work as well, and it may be, right, the first cut at a controller that works on uneven terrain. But because of the way I frame it, the control strategy is very sensitive to velocity disturbances. Because I designed the gait assuming I'm walking at a very specific speed such that the impact map that represents my transition from support of one leg to the next is valid. If you're slow down, that impact map is not valid anymore. And you have no control necessarily over whether the gait will proceed or not. So if you run the experiment in the lab and you put a barrier there and you slow the gait down, the robot risks falling over. And in the slow-mo, what I want you to see is it doesn't fail on the first step. So here's the contact. It completes the next step, but it's on that step that it's moving more slowly than the gait is planned for. And as a result, it can't finish. So it hits the barrier, it takes one more step, and then it can't complete the step after that because the impact map that we assumed is invalid in the presence of this disturbance. reason for this is basically there's no feedback on theta dot. There's only feedback on position. Well, we can solve, which drives us to solve, right, a different math puzzle, which is great because I'm not particularly good at this, but there are people like Russ Tedrick at MIT and now Toyota Research Institute who are really good at this, and Ian Manchester in Australia. And they developed this idea, well, why don't I provide feedback on the unactuated velocity as well as the unactuated position? And so you solve a more, so basically now you say, okay, well, if I think about that trajectory, well, there's actually maybe a funnel of underactuated states along that trajectory where I can drive myself back to the trajectory and I just need some feedback to tell me where to go. And so you can do that, and this isn't terribly important, but right, you're looking for the distance in the theta dot plane, the distance where you are from, say, that periodic trajectory. And that distance we're going to call I. And if we have feedback on that, well, now I can solve the more complicated math puzzle of how do I guarantee stability even in the presence of these velocity disturbances, which is great. And so, okay, we jump through, we can do it. And so now where we had previously just a PD controller, we have a PD plus, and I is not an integral term, so it's not KI. We have a feedback on that. But that is getting into the realm of truly math puzzle type solutions, because even with the computing power we have today, there's no ability to do a real-time computation of these gains or even this integral distance to calculate the distance I. You simply can't do it in real time for anything other than a two-link biped. And that's a toy problem. It's a great toy problem. People have built, Tedrick built a two-link rocker that walked beautifully with this controller. But you can't even apply it to it's never been applied to the experiment to even a three-link biped, let alone a five-link, and that's like on a boom, so we got to get to 3D. Plus, right, we've got gain scheduling, which means, okay, if you don't have a perfect model of your system, your simulated torques aren't going to be exactly the same as your experimental torques. And so now it heightens the importance of your system ID, which is inherently limited, particularly as your robot gets more complex. And then you've got to measure the zero dynamics velocity, which it's an unactuated velocity, and so you're going to use an IMU or something, some other remote or non-contact sensor, which means you're basically going to use an observer to get it, and it's noisy. Long story short, great math puzzle, cannot implement it in engineering practice. But my argument to you today is that, well, that math puzzle is actually really instructive for solving the engineering problem, though, because you can simulate it all day long, right? You don't care about the non-real-time calculations, so you can simulate it. And so what you do is you say, well, okay, what does the trajectory of the torso do under this control when I have velocity errors? And it's very predictable, right? So for red is a positive disturbance, blue is a negative disturbance, and for the torso, the response of this controller is pretty simple. And then if you look at the response of the swing leg, right, it's also very simple for the same strategy. And so in this case, you take the solution of the math puzzle, you simulate it, and you extract from it, well, what's the controller doing? And how do I approximate that with a heuristic? Well, first order approximation of these changes in trajectories are really pretty easy. So we take the provably stable controller for what it's worth, and then we, if you're a jazz fan, I would say we improvise on it. It's the melody of the song, and we do our improvisation on top of that melody, right? And in doing so, we've lost provable stability, right? In the same way that perhaps in a kinematics problem, we've lost the ability to exactly match precision positions. But I don't necessarily care about exactly matching precision positions, right? I care about generating the motion that I want. And precision positions might be the handy way of constraining that motion, but as I think Anurag talked about, relaxing some of those positions, right, to get the actual motion that you want, the same thing is happening here. And so, okay, we solve a different math puzzle to find out what's the feedback that's most useful. You don't really need care about this, but basically, okay, if we're going too slow, we lean forward and kick the swing leg out. And if we're going too fast, we do the opposite, but we never kick the swing leg backward because the swing leg's always got to come forward at some point to touch down. And so if we look at a simulation, because right, we can do all these controllers in simulation, we apply a disturbance, well now we can compare. The ideal is black, right? That's the transverse linearization feedback control. That's the provably stable one that has feedback on both the position and the velocity, and it's beautiful. So yeah, it takes the smallest number of steps, 2 at early gate cycle disturbances and 3 at later gate cycle disturbances to return to steady state. And if you just use hybrid zero dynamics, it's 6 or 5, so it's a lot worse in terms of return to steady state. But if you use our heuristic-based enhancement, well, we don't do quite as well as the black. We're in red here. But at some percentages of gate cycles, for some of those disturbances, we do. And if you want to look at, okay, how does it compare across gate speeds, it's the same story. HCD is the worst. Ours is somewhere in between. And the provably stable one here is the best. So what we're doing is we're saying, well, I'm going to seed my control design problem with the principles of the solution to a math puzzle. But I'm going to relax the constraints that make that a perfect solution to get myself a practical control. And so this is sort of phase plots for basin of attraction. We pay a little bit on efficiency to return to steady state faster. Uneven terrain is the whole purpose of legs, right? And so the idea here is our new controller is the velocity decomposition controller, and it can overcome stochastic terrain, where you imagine you don't have a vision system that tells you what the height of the terrain is, or you do have a vision system that has a certain amount of air, which is practically always going to be the case. And by improving the torso and leg regulation in light of these disturbances, based on a math puzzle solution, but not formally implementing it, we get better performance. And this is saying the same thing, right? So we have terrain height variation here on the x-axis and number of steps to failure here. So as you get up here, this is basically no failure for tiny terrain height variations. So the worst case is HCD, right? The traditional. Ours is in the middle, and the best case is the provably stable one out here. So we are approximating it in an implementable way. And we tried it on different terrain heights, and so here's some videos of, this is HCD and our approach. Keep in mind, transverse linearization feedback control can't be implemented in hardware. And so what you should be looking for here is there's a red tool chest, and the velocity decomposition hits it much faster, hits it earlier because it rejected the decrease in velocity associated with the steps better than the traditional. If we increase the elevation of those steps, right, we get to a point where the hybrid zero dynamics controller fails and our better one keeps going. And if we randomly throw the sheets of terrain height variation and different stiffnesses down, again, we see the enhanced controller, it's stable, and it's keeping the desired speed much more reliably than the traditional controller. And you pay for cost of transport. So, my argument to you is not that math puzzles are bad, right? My argument is, at least in my experience with walking, math puzzles are really useful up to a point. And where we get into danger with the math puzzles is when we're emotionally tied to them such that we're not willing to relax the constraints that allow us to get the solution and use the solution to inform a real engineering problem. All right, so optimization-based synthesis. So how do I do that? Mechanisms. Well, I've been interested in these shape-changing mechanisms for a while, primarily because I think they're a real engineering problem, and that's debatable. You might argue with me, and I'm interested in solving them both with rigid bodies and with compliant mechanisms, what have you. And the strategy we've been using has been basically optimization, right? We don't exactly match any positions. We're just trying to do good enough. And optimization is a handy tool for that. And specifically, we went to some trouble to find rigid body procedures, and then we said, well, how do we convert those, how do we use that rigid body information, because that seems like a lot of information we get, right? Honor, I was talking about the value of data. If we know rigid body solutions to a given problem, that ought to tell us something about the compliance solutions. And so we've tried using pseudo-rigid bodies to do partially compliant mechanisms, but that's a pretty logical connection between rigid body and pseudo-rigid body models. We've also used these to generate fully compliant mechanisms. And so from a rigid body synthesis standpoint, to some extent there's a math puzzle of, okay, if I want to match this surface of this mechanism, the green surface, to change its shape, well, it's possible that that green surface is entirely in the body of the mechanism, and so there's no ground pivots, and this would be like an open curve. It's possible that that could be a closed curve as part of a mechanism, where maybe there's, we looked at morphing dyes, and so there's maybe plastic flowing through the middle here, or if this were an aircraft wing, there's fluid flowing around it, and all these links have to be inside. But then it's also possible that that green surface I want to match is actually jointed to ground. And so we looked at the math puzzle, sort of a combinatorial math puzzle, right? What are all the possibilities that allow us to do this? And in our experience, right, so if you've got 2 points, 2 positions you want to match, and you want to put a slider on, right, it's pretty straightforward. And then if you want to add another dyad, right, you can find the center point. What we found was, as soon as we went to 3 positions, so 3 shapes we wanted to match, we never found good solutions for a slider with 3. So we always just said, okay, least square solution with 3. There are solutions, right? We know as kinematicians, there are solutions where I can find points whose 3 positions lie on a straight line. But we found that restricted the design space so much, we never got defect-free mechanisms out of our optimization. It's possible that they existed, but we never found them. And so we punted, right? We said, all right, well, who cares about exact matching? If we have three or more positions, we're just going to fit a least squares line. The same thing happened with circle points, right? With 3, you can always fit a circle, but when we got to 4, we never found good solutions when we constrained it to exactly match the 4. We over-constrained the design space because we were trying to exactly hit them. And so we punted to the least squares approach, and it works fine. And so we chose at the time a genetic algorithm, but maybe we'd use machine learning now, or some other optimization, particle swarm optimization, whatever your favorite optimization tool is, right? We minimized matching error, but we also thought about mechanical advantage, right? So how much torque do you need from your actuator to resist a load? And that's convenient in any optimization framework. And so we chose, our GA had a chromosome that contained all the information in the design. That's great. If you're designing a compliant mechanism, it's often the case that you'll establish this initial mesh network, right? And so you've got nodes, and then we consider connections between every possible node, and we do a combinatorial search optimization for this. And the key thing here is we alternate these as well. We basically discretize the design space so finely that we rarely allow the node locations to move, because it just becomes an overwhelming optimization problem if we have a huge number of variables and their positions are changing. And so that, as you get more and more of these, not only does the computational cost go up, but now you risk converging to a local minimum. And my argument in the abstract of this talk is that there's never going to be enough computational power for us, for the kinematics community. We're never going to be happy with what our electrical engineering and computer engineering colleagues give us in terms of computation. It's just never going to be enough. We'll always find ways to make more use of it. And so what we tried to do here was say, okay, well, we know a lot from the rigid body synthesis. Well, why don't we just take that topology and call it a compliant mechanism as if it were a pseudo-rigid body and just find the values of the beam length, beam shape, and cross-sectional design that match the same topology but are now compliant. And so, yeah, that works fine. We basically look at a bunch of topologies of the rigid body, and then we convert each of those to a compliant mechanism. You make it a two-step process. It's better though, right, if instead of, for a compliant mechanism, you have this complex network, just take the topological network from the rigid body solution and make that the initial mesh of the compliant mechanism. You've thrown out a ton of possible solutions, but you've gained more flexibility in other cases because now, right, you can allow binary variables, so not every one of these links has to be present. Right? You can allow them to disappear. You still have the ability to control beam length, beam shape, and cross-sectional dimension. And so ultimately, by taking the idea of, well, what's the topology of a rigid body solution that does pretty well for this particular problem, using that to generate the compliant mesh network, and then using that smaller mesh network with fewer design degrees of freedom, but maybe better resolution on it to generate a better solution. There's no math puzzle here, right? We basically jettisoned all of the math puzzle pieces of this. It's not elegant. It's not insightful beyond the idea that, well, the topologies of the compliant mechanism and the rigid body mechanism actually share some understanding of the problem. And so you have to jump through some hoops, you have to solve some other math puzzle to say, well, get rid of the disconnected topologies and the invalid substructures so you're not searching invalid solutions, which Anurag talked about, right? You feed the machine learning algorithm the defect-free mechanisms already. So there's some interesting kinematics there to be done. But ultimately, right, if we don't allow the topology to vary, we get a complicated mechanism. We actually get a much better performing and simpler mechanism if we shrink our design space from the complex mesh network, informed by what we already know a priori about the problem. So that's what I'd originally planned to talk to you about, is why I think searching the design space, even as our computational power improves, why I think shrinking the design space often leads us to better solutions if we shrink it in an intelligent way. But then what I ended up wanting to really talk about was, are we solving math puzzles? And to some extent, you could level a critique that some of what I presented today was solutions to math puzzles. Math puzzles are great, they're fun, I like them. Sometimes they overlap with engineering problems. But that's where I think we as a community need to focus our effort, is where they do meaningfully overlap, where they do at least have potential to overlap. And I think we need to let go of some ideas that over 30 years haven't shown the overlap that we hoped they would. That's all I have to say.
Thank you for that fascinating talk, Jim. I think it was a good closure because yesterday we started with walking machines by Professor McCarthy, and today, we are ending it with walking machines. And before we walk out of here and close this summer school, there are a few items on the agenda. However, first thing is questions for Professor Schmiedeler. Any questions?
Let's just close out the agenda.
I know. Professor Schmiedeler is very efficient when it comes to closing the meetings. We love him for that. Okay, so the few items on the agenda are: number one, there is a survey on the school's website. So if you have your laptop or your phone, whatever, please go on the website. If you don't remember the URL, I will tell you, it's very simple. It's tiny, Tiny,